All right, thank you so much. It's a pleasure to be here today. My name is Jose Cortes, and I'm a researcher at Edinburgh University. Let me share my slides. Okay, so today, as the corresponding author and on behalf of my co-authors, I'm here to present a linear pulse frequency modulator ISFET with a wide supply range. A little bit about the content of this presentation. I will briefly give an introduction about the motivation behind this research, and then I will talk about the technology I have been using, an overview of the ISFET theory and instrumentation. Moving along, I will describe in detail the proposed sensing architecture and some of the results, both in simulation and actual measurements so far, to then give the final conclusions about the benefits of this design. All right. So in the last couple of decades, pH monitoring has gained great relevance as a fundamental parameter to ensure the safety of multiple solutions and environments for different applications. From environmental water quality to food waste through the composition analysis, pH detection has been extensively studied through multiple sensing platforms. More recently, pH detection for implantable applications have been of great interest, and some devices have shown great applicability in forms of capsules and wearable devices for sweat monitoring. However, most of these applications share common problems like low reliability, signal processing for wireless transmission, and difficulty to detect sub-pH levels, especially for in-body pH detection. In the last decade, the integration and miniaturization of CMOS electrochemical sensors has focused its efforts on the development of sensing and biomedical devices, taking advantage of the speed and low cost of fabrication. One of the applications of interest is the use of ion-sensitive field effect transistors, or ISFET, to detect electrochemical signals, such as pH, using small-size, low-power devices with high sensitivity. But what is an ISFET? An ISFET can be described as an electrochemical sensor that follows the behavior of a MOSFET transistor with the gate exposed to a solution and a constant and well-known voltage provided to a reference electrode, which is needed to make accurate measurements and can be used to calibrate the working region of interest. The interface between the concentration of ions in a solution and the gate generates an ionic distribution near the surface of the passivation layer based on the Gouy-Chapman-Stern model, which can be modeled as a couple of capacitors connected to the gate, as well as an extra passivation capacitance due to the surface layer. ISFET circuitry fall into four categories: pH to voltage, current, time, and frequency. The most popular pH to voltage topology is the source drain follower because of its compactness and low power consumption. However, it lacks compensation schemes and it is dependent on power supply variations. Regarding the pH to current category, a CMOS current mirror and a translinear principal architecture stand out. Drift, temperature compensation, and gray linearity cover their advantages, but they carry issues related to the simplicity and or complexity of each design in terms of size, power consumption, and compensation schemes as well. CMOS inverters are the main base circuitry for the pH to time approach. Advantages include less susceptibility to noise, less signal processing, small size, and low power consumption, as well as compensation schemes for non-idealities. However, all of them are open loop inverters, making them very susceptible to PVT variations, and some present minimum pulse width variation, making it less suitable for sub-pH applications. Lastly, the most prominent approach in recent years has been the pH to frequency conversion. These designs can have multiple advantages in terms of size, power consumption, linearity, signal stability, noise, and capacity scaling. However, some disadvantages fall into nonlinear responses and PVT variations for the open loop designs. Moving on to the sensing architecture, the schematic shown in Figure 2 presents the front-end architecture, which consists of a voltage to current converter, a bidirectional current integrator, and a control circuit for the feedback, allowing the charging and discharging of the membrane capacitor. The ISFET corresponds to the positive input of the OTA amplifier in the voltage to current converter. This configuration allows the signal to be encoded in the frequency domain with a linear response to pH changes. The sensor was implemented in 0.18 micrometers technology, and the layout is shown in Figure 3. The sensing area corresponds to an extended gate electrode of 125 micrometers by 125 micrometers. The readout instrumentation is complemented by two bias current sources and a programmable gate capacitor for trap charge compensation. The main advantages of this sensing architecture relies on 6 points. The voltage to current conversion allows a linear response due to the capacity to control precisely the current that charges and discharges the capacitor at the same rate. Furthermore, it allows an extended operating range close to the power supply to keep a wide linear range, and therefore less calibration is needed. This design provides a digital robust output of fixed duty cycle, reducing the consequent signal processing for data manipulation. The adjustable frequency feature allows for an increase of the dynamic range, making it suitable for sub-pH detection, and the system can get a steady response of the frequency even with a 25% variation in the power supply voltage. Finally, the design shows high immunity against noise due to not being dependent on the power supply variations. Simulated results shown in figure 5a demonstrate an output response with a 50% duty cycle, proving the correct functionality of the architecture as well as the charging-discharging phase of the membrane capacitor. The frequency variation depending on the voltage range between V height and below is shown in figure 5b. The lower the difference of the voltage, the faster the frequency response, reaching a maximum output of 2.3 megahertz at the rate of 683 kilohertz per volt. An electrical characterization performed on the fabricated chip shows the linearity of the system with different differences of voltage and also a close matching with the simulated data. A Verilog A ISFET model was incorporated to the design to evaluate the behavior of the frequency for pH values. Vin represents the voltage going into the gate of the ISFET. Figure 5c shows the output frequency from pH 1 to 14, considering a silicon nitride sensing layer as a 30 millivolts per pH sensitivity response, according to the literature. Figure 5d presents the response of the circuit for a wide variety of supply voltages. This is important for wireless implant applications, where the received power can vary widely depending on the position and orientation of the sensor. The results show that even though there is a small drop in the output frequency, the circuit can work robustly down to 1.4 volts. Furthermore, the circuit was simulated for transient noise with different scale factors. Figure 5e showed the temporal response for an expected value of 473.6 kilohertz output for pH 7, with a minimal average variations of 200 hertz. Similar time domain noise simulation is used to plot the power spectral density for 3 pH values in figure 5f. The fundamental waves corresponds to the expected frequency for each pH and can be easily distinguished. A Monte Carlo analysis for mismatch was performed to analyze the response of the entire pH range in 50 runs each. The resulting histogram plot is shown in figure 6. The mean frequency remained close to the expected value for each pH with an average standard deviation of 567.76 hertz, showing great consistency against mismatch variation. However, process variations can still affect the output response. This can be reduced by using the adjustable frequency feature to isolate the peaks, or by using an array of pixels to get an average of a group A data instead of single data points. Finally, several tests have been performed in the last couple of months to demonstrate the sensitivity of the sensors for different pH values. It's important to notice that we achieve a much lower sensitivity than the expected result, corresponding to 3.14 kilohertz per pH, which transduces to 5.44 millivolts per pH, far away from the 30 millivolts per pH used in the Verilog A ISFET model. Among the probable causes for this drop in sensitivity, we identify two main components. On one hand, the programmable gate capacitor we incorporated is being used to calibrate the working range of the frequency response, but evidence has shown that this benefit comes with a decrease in the expected sensitivity at the output. On the other hand, The type of technology we are working with varies from most of the literature evidence, as usually the literature contemplates an AMS 0.35 micrometers process. TSMC 0.18 micrometers base technology consists of a 6-metal layer process, has a different arrangement of some components, specifically capacitors in the metallic layers, and has more restrictive layout design rules, opening the window for some unexpected negative effects in the corresponding sensitivity. To conclude my presentation, this work has introduced a low-power linear PFM architecture capable of encoding a pH signal in the frequency domain with a wide linear range. The architecture provides an average sensitivity of 17.3 kHz per pH with a linearity of 0.99 and an average standard deviation of 567.76 Hz. It works with a very wide range of supply variation for long-term duration, and the programmable feature allows for an increase of the dynamic range, making it suitable for sub-pH detections. To conclude, I would like to thank the CDT in Intelligent Sensing and Measurement, QuantaSeed, and the I2T2 for the economic support and academic support provided for this research. Thank you very much for your attention. I'm happy to take some questions from the audience now.